Aline, if you agree, we can start. I will start recording. Okay, good morning, everybody. This is a new colloquia by the Instituto de Astrofísica de Andalucía here in Granada, in Spain. And today we will have the talk by Dr. Aline Vidotto, and she will talk about stellar winds and their interaction with exoplanets. Dr. Vidotto will be properly introduced by Isabel Marquez. Isabel, please.
Hello, everybody. Thank you very much for attending this new weblogium from the Severo Ochoa program at the Instituto de Astrofísica de Andalucía. And first of all, thank you very much, Aline Vidotto, for accepting our invitation to give this talk, which is going to be extremely interesting, I'm absolutely sure. Aline Vidotto is an associate professor at Leiden Observatory in Leiden University in the Netherlands, and she is the principal investigator of the consolidated grant from the European Research Council called Astroflow, which investigates the interaction between stellar and planetary outflows. Prior to joining Leiden in 2021, she was an academic at Trinity College in Dublin in Ireland. And previously, she has held independent research fellowships from the Royal Astronomical Society in the University of St. Andrews and from the Swiss SNF at Geneva Observatory. Her research group studies the interaction of exoplanets with the host star's wind and how this interaction can affect planetary atmospheric scape. For that, her group develops sophisticated 3D simulations of winds of low mass stars, which permeate the entire exoplanetary system. The realistic account of the wind has supplied more detailed diagnostics of its interaction with exoplanets, guiding observers towards the most promising systems to host detectable signatures of such interactions. This is in fact the subject of her talk today, stellar winds and their interactions with exoplanets, with the aim of reviewing this subject and also providing a context of what we know from the closest star to us and its planetary system. Thank you again, Aline Vidotto, for accepting an invitation that I'd like to extend to a real one for the future. So we will explore the possibility to invite you here at the IAA in person. Thank you very much again.
Thank you very much. Thanks, Isabel. Thanks, Miguel. It's a pleasure to be here. Thanks a lot for the invitation. So since I started with my thanks, let me also thank the people who have worked on the project. So I'll be talking today about how stars and planets interact with each other. And I have a number of people that have worked with me on this. Right, so just before I start, to contextualize, when I say stars in this talk, I'm concentrating on stars that are similar mass of our sun or lower masses. So these stars, they have activity. And activity, they can come in different forms. One form is that they can produce high energy radiation. So radiation that comes from flares or from the corona, for example. They can also produce particles. The stellar wind is an example of this outflow. And a stellar wind comes in more quiescent phase, but when the star is very active, they can also eject these bursty, episodic bursts of coronal mass ejections. So together, we call this the space weather that is shaped around an exoplanet. So before I start, let me just put it in context. A little bit of the evolution of this activity. So on the right-hand side here, I have a plot showing the luminosity in X-ray or in UV as a function of age. Without caring too much about the differences in the lines, you see that in general, there is a decay in high energy radiation from the star as the star gets older. You can also see this in the particle part of this activity. So you have here a plot of mass loss rate as a function of X-ray flux. And you see here that the stellar wind is stronger when the X-ray flux is higher, or in other words, when the stars are in general younger. So the first lesson we have from this is that the younger the star, the higher the rotation rate, the higher the activity, the higher the high energy radiation, and also the stronger the wind. This is actually a very interesting feedback loop between age, rotation, and magnetic activity of the star. Now, having said that, even we know that the younger the star, it will the planet will experience a harsher environment. However, it does not necessarily need to have only a young star. Imagine that you are orbiting an old star or middle-aged star as our sun, but instead of you orbiting at 1 AU, you bring your planet very close to the star. So I have here for comparison the orbital distance of a hot Jupiter. So typically we go from 200 stellar radii of distance between the star and the planet to 10 stellar radii. Now, when you bring the planet closer to the star, even if the star is old, you have higher density coming from the stellar wind, higher magnetic field, and also you get more radiation. Now, the second lesson is that even if you're orbiting an old star, you still get harsher environment if you're a planet orbiting close to the star. So, of course, if you're a planet orbiting close to a young star, then your environment might be even more extreme. Now, let me now move on to what I want to talk. So I'll start with talking about radio emission, so how we can constrain star-planet interaction, looking at radio wavelengths. Then I'll move on and talk about Atmosphericscape and how it evolves. And then finally, I'll combine the 2 points and I'll move on with Atmosphericscape and interactions with the stellar wind. So regarding the first one, we believe there are at least 2 ways that radio emission can be generated in a star-planet interaction. One comes from the planet itself, so we call this auroral emission. So this is also what we see in the Earth when we see the northern lights, or for those of us who grew up in the southern hemisphere, the southern lights, I would say. And also the second emission is an emission that is occurring at the corona of the star, but is induced by a planet. I'm gonna talk a little bit about both of them. So starting with the auroral emission, the idea here is that the emission occurs at the poles of the planet. And I have this movie that illustrates the interaction between the solar wind coming from the left and the magnetic field lines of the Earth. So what you see here in the night side is the magnetic field lines of the Earth getting closer and closer together until they touch. There's a reconnection event, and this reconnection then accelerates electrons, and these particles then spiral along the magnetic field line. So this process is known as electron cyclotron, a maser process. And the cyclotron here is actually the key word we are looking, because if you remember, the cyclotron frequency is proportional to the magnetic field. In this case, if you measure this process, you identify it comes from an exoplanet that has a magnetic field. If you measure the frequency, then you can use this equation to infer the magnetic field strength of the planet. So for example, a magnetic field between 1 and 10 Gauss will generate emission around 13 megahertz. And it's interesting that if you look in the solar system, so these are the points here shown by filled circles, the moons are the open circles. In the solar system, if you plot the amount of auroral emission, the power of this emission as a function of the power of the solar wind that arrives, that is dissipating in the magnetosphere of the planets, you see that there is a more or less linear relationship. Now, remember that I told you that if you bring your planet much closer to the star, the stellar wind becomes stronger. So we believe that if you have an exoplanet orbiting very close to its star, the wind power is going to be stronger, and therefore the radio power this planet would emit, assuming it obeys this relation, is going to be several orders of magnitude larger, much larger than Jupiter, for example. Now, the question that we don't still know precisely the answer is, what is this incident power for any planet out there? So one way that we compute that in my group is using numerical models. So I'm going to present the work by one of my PhD students, Robert Kavanagh. So what we were looking here, we were modeling this system. Is very famous in the exoplanet community, HD 189733. It's a K dwarf that has a close-in hot Jupiter. So what is special in this study is that we knew from different observations the magnetic field topology of the star. So what I show you here in the top row is the magnetic field of the star at different epochs. So it's more or less 1 year apart from different epochs. And then below is what we get when we use these magnetic fields in our numerical simulation. So the idea here is that these magnetic fields, they provide the boundary condition for the simulation. So they are fixed at the surface of the star. And then as the stellar wind outflows, it interacts with the particles and then it shapes this environment surrounding your planet. So I have here the 3 solutions for the stellar wind in the equatorial plane. And these crazy lines are the magnetic field lines from the star. So these 3 simulations, they are all identical except from the map that we input in for the star. So the magnetic field is changing from these 3 years. And now we did the following experiment. Using these numerical simulations, we calculated what would be the stellar wind energy or power, and then we computed from this power what would have been the emission of the planet if the planet was following this radial relationship for the solar system. And what we have here is the flux density in radial of this particular planet as a function of time. So these are for our 3 different simulations. We don't know the magnetic field of this planet, so we assumed that it is 10 Gauss. And what is interesting here is that if you look at these 3 points, they are all above what the LOFAR detection limit is at this particular frequency. So there is something happening that we know in this collaboration. We also had LOFAR observations of the system, and these observations provided no result, so there was a non-detection. So there is something happening that is preventing the escape or the emission to escape the system or to be generated. And there is a number of ideas of why we don't see the emission. And I'm not going to go into the details of each one of them, but I wanted to highlight one of them, the last one. So this emission comes in a cone. So there is a hollow cone, and it acts like a lighthouse effect. When the cone of the emission passes in front of along our line of sight, then we see a peak in the emission. So if maybe you don't observe at the right time, you don't see this emission. There is a very great news for the community. So earlier this year, LOFAR has detected bursty emissions from Taubu. So the results were reported earlier this year, but I think the data is a couple of years old. Now, this emission happened between 15 and 30 megahertz, and we hope it is planetary radio emission. The authors were very careful in not announcing it as a radio certainty with 100% certainty, but if indeed this is confirmed by follow-up observations, that would be the first time we observed this sort of observations. We have this sort of emission. So there has been other hints in the literature, but to my knowledge, most of them were not 100% sure. Now, if this is indeed emission coming from the aurora of the planet, then we can place constraints on the magnetic field. So investigating star-planet interactions can also help us to further characterize the planetary system. Now, the second type of radio emission that I would like to discuss is the emission that is induced in the corona of the star. Now, what we are doing here, we are replacing Jupiter by a star, and we're replacing the moon Io by a planet. Now, the idea is that when the moon is orbiting around this planet, there is a connection between the moon and the star. Essentially, you have some sort of waves known as Alfvén waves that propagate along these magnetic field lines, and these waves dissipate and then emission is generated. Now, I'm going to come back to this point, but this emission happens when the planet is very close to the star, and I'll come back to this in a minute. But similar to the emission I mentioned before, this is also a cyclotron process. And therefore, if it's a cyclotron process, we can relate the frequency that you observe to the magnetic field. Now, because the waves are traveling in the magnetic field lines of the star, so the magnetic field lines, the magnetic field strength that we have in this equation is the stellar magnetic field, not the planet anymore. So now, the stars, they can have a stronger magnetic field, so it means that you can observe at higher frequencies. So in this case, for example, if you have observations between 120 and 160 megahertz, you're probing the region of the magnetic field where the strength is between 40 and 60 Gauss. Now, the study I was talking to you before, we were looking at HG 189733, and it's a K dwarf. Now we're going to look a little bit, move towards the M dwarf. So these are smaller stars. And there has been some real great news in the area as well on detections of planet-induced emission. And I cite here two M dwarfs. So GJ 1151 was observed with LOFAR. Again, this process generates highly polarized emission. So this star was observed with highly circulating polarization. And the authors discuss several mechanisms that could have generated this emission, and they conclude that it's more likely to be an unseen planet. So there is no planet detected in the system so far. But the idea is that this planet would be the cause of this excess emission in radio. And your very own, Miguel, as well, has worked on the emission of Proxima Centauri. So this is now in a higher frequency. And also they say that this is consistent with emission coming from a planet. Now, in the case of Proxima, we know the planets, there are planets in the system, we have detected them. And in a couple of weeks ago, there was also the announcement of a survey. So we're looking here at these new detections in radio that are shown here in black. Again, these are all M dwarfs. Now, this plot shows the luminosity in X-ray as a function of luminosity in radio. And there is a correlation between LX and LRAD that we know for some decades now. And these stars, they seem to be over luminous in radio. So if you take, for example, a constant, certain value of Lx, you would expect these stars to be showing radio emission, for example, at this range, but they are actually showing radio emission at much higher values. So these stars are apparently inactive. And again, the authors suggest this could be emission caused induced by a closing planet. Now, for us that we do simulations, we went on to look into more details on the emission coming from M dwarf. So I'm again showing another paper from Robert Kavanagh. So what we have here is the magnetic field map of Proxima Centauri and the magnetic field map of AU-MIC. So AU-MIC is very young, it's around 20 million years. So they are both M dwarfs. And the magnetic field strengths, they are quite larger compared to the other system I showed you before. Now, what I show you in the bottom panels is the stellar wind properties. So you're looking at the star at the center, magnetic field lines, and then this ugly surface that we call the Alfvén surface. So the Alfvén surface is essentially telling us that within this boundary, interior to this boundary, the energy of the magnetic field is much stronger than the kinetic energy of the stellar wind. And outside this boundary is the opposite. So the kinetic energy becomes higher than the magnetic energy. And that's important because if you're within the Alfvén surface, and that's actually the key point for us, if your planet is orbiting within the Alfvén surface, it means that you can transport information back to the star. If your planet is orbiting outside the Alfvén surface, then this information cannot go back to the star. So if you want to have emission that is induced by a planet, you want to put your planet inside the Alfvén surface. So in this particular stellar wind, at this particular date, with this magnetic field map, the planet is outside the Alfvén surface. So in this case, the planet was not inducing radio emission according to our models. And on the other hand, if you are aeomic, you can then, because part of your orbit is inside this Alfvén surface, you can then trigger some waves that will propagate towards the star, and then emission can occur. So what we did further, we looked at what would be the spectra that would be generated from this interaction. So you have here aeomic, and we are just illustrating the field line that is connecting to the planet as the planet orbits around the star. Now, one of the things that we need to take into account is that for this emission to occur, we need to have the cyclotron frequency larger than the plasma frequency. And this region, it doesn't occur along the whole magnetic field line. It only occurs around the portion that is shown in blue. So if you only take this blue region and you compute the flux density coming from this interaction, we can then generate a dynamic spectrum. So this is flux density versus orbital phase, and the color is the frequency. And highlighted here is the 140 million hertz. The gray area here is when the planet is outside the Alfvén surface, so we don't compute the emission in that region. Now, we can compare with observation. Of course, we are not talking about the same star. It's a different system, but it's interesting that it's not actually too different from what is predicted in our models. But of course, as I said before, this might be just a coincidence. Now, what is really interesting for me is that we know the dependence of the cyclotron frequency and the plasma frequency with properties of the stellar winds, such as magnetic field and density. Now, for us, that's a cool way that if you detect this emission, you can then constrain the mass loss rate of the star. And that's what we did in this paper here. Now, in the second part of my talk, I will talk about Atmosphericscape. So I'm moving a little bit off topics, but I'll come back to the stellar wind in a bit. So we think that atmospheres are relevant for habitability, and atmospheres are also atmospheres on Atmosphericscape are also relevant for shaping the population of planets. So you have here the histogram showing number of planets as a function of radius. And you see that there is a valley here in this histogram. We believe that planets here, they were born with a bigger, larger volume of atmosphere, but they evaporated to such an extent that they piled up on the other side of the histogram. So atmospheres are important for planets for many reasons. And we can detect atmospheres in a couple of ways. I'm going to show you what I call the direct way. So we are looking here at transit. So you have your star, you have your planet, and when the planet blocks part of the light of the star, you see an absorption. Now, if you look in broadband, your light curve has this particular transit depth. But now, when we look at a particular wavelength, so let's suppose your planet has a hydrogen-rich atmosphere. So we can look in Lyman alpha lines that captures the neutral hydrogen on the atmosphere of the planet. If you want to measure your planet, the atmosphere, you can do what is called transmission spectroscopy. That is essentially letting the light of the star be transmitted through the atmosphere of the planet. So my really simplified version from a theorist of how you do that from observations is that you take a spectrum of your star when the planet is not transiting. You take another spectrum of the star when the planet is transiting, and then you divide the two, and you see how much got absorbed. And if you plot that in for example, in this Lyman alpha line, you see a transit that is much deeper. And I'm going to talk a little bit about this particular spectroscopic transits. So we have now several detections in Lyman alpha. This particular case for me is still the most wonderful and a very extreme case of a small planet, a warm Neptune orbiting a small star, an Aurora. Well, the planet is not too small, sorry, it's a warm Neptune. So you see here the light curve, and the light curve in the optical light is this tiny little dip over there, and this is the big light curve transit when you look in Lyman alpha. And the idea here is that this planet loses a lot of mass, and this material is distributed around the system, and therefore they are absorbing a lot of photons from the star and causing this strong extreme transit. Now, the problem with Lyman alpha is that you have to go to space, so it's not the most convenient way to observe a bunch of planets evaporating, but we also have very good news in the area. From the ground, you can observe the infrared triplet of the helium-1, and we have had observations now of several planets that are evaporating, and we are looking into helium lines. So I have here again 2 illustrations, WASP-69b and WASP-107b. One is done from the ground with CARMENES, and the other one here was done with Hubble. Now, the common features that we see in these helium observations is that the star is relatively active, so it has a large UV flux to lift the atmosphere. Now, this evaporation or photoevaporation is usually modeled with hydrodynamics. So the idea here is that you have your planet, your rich the hydrogen-rich atmosphere, and you have photons coming from the star. So these photons have to be above the ionization threshold for hydrogen. So you're looking here in the UV and in the X-ray. So once this XUV photon reaches your planet, it can ionize the hydrogen. And the excess energy above the ionization threshold is then used to accelerate the particle. So essentially, you're converting it into heat. And this heat increases the temperature of the atmosphere. So if you increase the temperature, it more easily expands and therefore evaporates. Now we can, coming back to this plot I showed you at the beginning, we know that earlier ages, there is more XUV luminosity than at older ages. So your planet is receiving a higher flux, even if the orbit is not moving. And we can then show through different models, and I'm going to highlight a couple of works done here in my group on how this evaporation can affect the evolution of the planet. So in this one, we are looking at how escape affects the internal structure of the planet. You have the radius of the planet versus age, and we borrowed the code MESA, which is done for stellar evolution, and we use this as a planetary evolution tool. And you can compare, let's just look at this line and this one. You can compare the case where no escape was considered with cases where escape was considered. And you see that by adding escape, you change quite substantially the size of your planet and the evolution of this size with age. So escape indeed affects the internal structure of the planet. I like to think of this similar to stellar evolution, where if your stellar wind is too strong, you can also affect the life of your star, and thinking in particular regarding massive stars. The other thing that another study that we did is that if you place your planet orbiting these different stars and you calculate their evaporation, so here we have a planet that is about 0.3 Jupiter masses, you see that the escape changes quite a lot, right? So you go from 10 to 13 to 10 to nearly 10 to 10 grams per second from 10 to 4,000 a million years. Now, if you integrate these curves below with age, so you can actually estimate the amount of atmosphere that is lost. In this particular case, there's a substantial loss of atmosphere in this particular study that we did. But of course, there are cases that the atmosphere could be totally evaporated. So it's also important for the survival of atmospheres to understand the UV history of the star. In this particular work, we also did some predictions of what we would observe, what would be the Lyman alpha and also the H alpha spectroscopic transit we would see for these systems. And the colors here, they show age. So we have the two lines, and this is the transit, the amount of absorption you see during the transit. And the color here indicates age. So the younger the star and the planet, the darker is the color. Now, what you see is that at the younger age, you have broader lines, Lyman alpha, quite saturated, the line center. And in H alpha, we also have excess transits in the order of 3 to 4%. So this is good for observing, but you also know that when the star is very young, it's also very active. So there is a lot of H alpha fluctuations happening. So it becomes more difficult to disentangle whether this is coming from escape of the planet or whether it's coming from the star. Now, but one of the criticism with this work is that we did not consider the presence of stellar wind, and this leads us to generate these symmetric lines when we know from observations that these lines, they are not symmetric. And the reason is, then I move to my third part of this talk. The reason, one way for you to remove this symmetry on the lines is to change the geometry of the amount of atmosphere around the planet, or the whole geometry of the atmosphere. So you have your planet here. This planet starts to evaporate because of the high dose of XUV radiation. But in addition, you have the stellar wind that shapes this outflowing atmosphere. So I'm going to show from now on some of the results of my group. And just before I start discussing and I forget, so I'll be concentrating on these papers by Stephen Carlin and also by Gopal Hazan. Now, in our previous works, such as the work I showed you before, we were using 1D simulations. And because they are 1D, they are spherically symmetric, and we can't include stellar winds on them. So if we move to 3D, then we can use more complex interactions, and that's what we are doing. So in this particular study, what you have here is now the planet, no longer the star. And these field lines are actually velocity streamlines. So I'm showing here simulations that don't have magnetic fields. The ones that have magnetic fields will show towards the end. So the stellar wind is injected in the grid, and this stellar wind interacts with the planetary atmosphere that is escaping. And therefore, you have this different shape. So the stellar wind field lines, velocity field lines are shown in white, and the planet is shown in black here. So let me just show this in a movie. So this is a cut in the equatorial plane. This is the planet. The atmosphere of the planet is evaporating, but there is no stellar wind. I'll turn on this movie, and then you see how the stellar wind changes this spherically symmetric or nearly spherically symmetric distribution. It's not completely spherical because there is a night side, there is a shadow in the night side of the planet. Now, my planet here, we are moving in the orbital frame of the planet, but the orbital motion, just for reference, is pointing up in the screen, and the stellar wind is coming from the left. So let me turn on the simulation. So what you see is that as soon as the stellar wind is injected in the grid, you see the formation of several hydrodynamic structures. One of them is this tail that looks like a comet-like tail, and this tail is shaped by the interaction with the stellar wind and also by the orbital motion. And you can also have a bow shock. If the interaction happens at supersonic velocities, you can also have a bow shock formed ahead of the planet. Now, one of the studies, this is also work done by one of my PhD students, and one of the studies we did, we wanted to see how much or what would be the change in the escape of the atmosphere if we changed the property of the stellar wind. So we had a controlled experiment here where we had the planet at the center. The stellar wind, again, is coming here, is coming from the left in each panel. And again, this is a 3D file that I just caught in the plane for easy because it's easy for us to see. And the difference between these three panels is that the stellar wind mass loss rate is twice the value of the solar wind, and it's 10 times, and then it's 20 times. And there is like a tiny white line around the planet. That's what we call the sonic surface. I can come back to this if anybody has questions, but the idea is that if you look at the sonic surface, as we change the mass loss rate of the stellar wind, the sonic surface starts to be disrupted until they merge with the outer sonic surface we had before. And what we realize is that once this happens, once this sonic surface is disrupted, we end up having atmospheric escape rates that decrease instead of increasing. So the stronger the stellar wind, the lower the escape rate. That's one of our findings. But what was more actually important for us is that you see that the volume occupied by this atmosphere also decreases substantially. And this affects the signature from the observations. So if you calculate the amount of absorption that you would see in Lyman alpha versus the atmospheric rate, you see that the case that have no stellar wind involved have the largest Lyman alpha absorption. Now the escape rate here, so I'm moving from right to left, and as I move from right to left, I'm increasing the mass loss rate. So here is no stellar wind, so 0, then this is 2 times the solar value, up to 100 times the solar value. So what you see here is that even though I'm increasing the stellar wind, there is not much happening to the escape rate of the planet. Once I disrupt the sonic surface, then we have a reduction in escape rate. Now, even in the case where nothing was happening to the escape amount of planet atmosphere escaping, you see that the amount of absorption was changing substantially. And this is interesting because if you have your observation and you want to include stellar wind effects to be able to derive atmospheric escape rates more accurately. Now then come to this kind of what I call a dichotomy. So I already mentioned to you Eumic. So Eumic is a young pre-main sequence M dwarf. It has an orbiting planet that was discovered last year. And now you imagine you're this planet, you're orbiting a young star that has a lot of UV flux. So you imagine it will have a lot of evaporation. But we also know that the younger the star, the stronger the wind. And there are works that suggest the winds of this star is between 10 and 1,000 times stronger than the solar wind. And I just told you that the wind could reduce the evaporation. So we are faced with a choice, which one dominates? I don't have the answer for you, but we did look into this more carefully. So we have here just 2 simulations showing the stellar wind that is 10 times solar and the stellar wind that is 1,000 times solar. Now, we did not find a lot of reduction in terms of evaporation, but we do see a lot of Lyman alpha reduction in Lyman alpha transits. So in the case where the stellar wind is very strong, we essentially erase the signature of the planetary outflow because of such a strong stellar wind. Now, this can be seen in a negative way, but I also believe we can spin this for a different use. So if you measure transits, so this is again the observation of GJ436b in Lyman alpha, and you model these observations, and we have here the work done by Carolina Villarreal D'Angelo. So what you see here is that if you just these 2 lines, they have the same amount of radiation, but they have different stellar wind properties. One does a better job at fitting the observations than the other. So if you can incorporate observations and modeling, you'll be able to learn more about the system, not just the atmospheric escape rate, but you can also learn about the local stellar wind properties. So that's the flag I want to raise here. Exoplanets, they can actually be used to probe stellar winds. Now, I mentioned these quiescent stellar winds, but there are also phases in the life of a star, and we see this in our sun, that the sun is more active and has these events of coronal mass ejections. So these are a huge amount of particles that are released from the surface of the sun. And I want to come back to this system 189733. So this is observations of the system done in 2 different epochs with Hubble in Lyman alpha line. So there was no excess transit in Lyman alpha in one particular epoch, and a year and a half later, it seems that there was a lot more Lyman alpha transit happening. So the interpretation was that the atmosphere of the planet started to evaporate. Now, coincidentally or not, in the second epoch, just 8 hours before the transit, a flare was detected on the star. So then we have this question, whether is the flare that is enhancing the UV radiation coming to the planet, and therefore the planet starts to evaporate in September 2011, or is the coronal mass ejection that once this material passes, it actually erodes the atmosphere of the planet, and therefore you see more of the atmosphere evaporating. To study this, we also used our models and we simulated several scenarios in 3D. I'm showing you one scenario that is the quiescent scenario. So this is the planet, this is the density. So in this quiescent scenario, you have a normal flux for the XUV, you have a normal stellar wind, and also we have the active state where we increase the knobs in our observation. So we increase the flare, we increase the energy, and we also increase the flux of particles that arrive that impact the atmosphere of the planet. And just by looking at the color code here in density, you see that this density here is larger. So if you calculate the evaporation rate, the amount of mass that is being lost, we can then see how each individual flare and CME, each individual event affects the planet. So we have in our simulations a scenario, the quiescent scenario I showed you, and the extreme CME active scenario I showed you, active plus flare, and we also have in between events. So does stellar activity, in particular flares and CME, affect Planetinduced? From this plot, we see yes. But one of the things that we realized in this work is that the flare alone, it did not change the evaporation so much. It was more the CMEs that was more effective at removing the material momentarily. So CMEs are also expected to be more frequent when the planet is young, when the star is young. Therefore, we might also need to include them in future models to interpret observations, especially if your planet is orbiting younger stars. And to finish, I would like just to show our recent work on converting our simulations that were hydrodynamical into magnetohydrodynamic. So this means that we include now the magnetic field of the planet and the magnetic field of the stellar wind. And when you add magnetic fields, things become more interesting. One of the things we immediately see is that the dynamics of the escaping atmosphere changed. Right, so you see now the magnetic field lines of the planet form what we call a dead zone in stellar wind theory. So essentially you have particles that get trapped inside this equatorial region. And you also have polar flows. So this image is 3D and we might not be able to see very clearly, but there is also the counterpart of the north polar flow in the south here. So this actually leads to the formation of two tails. So if you compare here the density, so this is on the left is total density, and on the right is just the neutral density. And we want the neutral density because we can compute the transit in Lyman alpha with this one. And on the top row, you have the case without magnetic field, and this is the case with magnetic field. Now we are in the plane of the sky. So again, your planet is orbiting your star, and the star is in the left of this screen. And you see here the comet-like tail when there is no magnetic field included. And here you have now the formation of these extra tails, these two tails, when the magnetic field of the planet is increased. And what is interesting to imagine now is that this becomes a little bit more complex, because if you look, the tail in the north is not exactly the same as the tail in the south. And this is because of the different orientation of the stellar wind magnetic field. So because of this difference, if your planet transits, let's say it's grazing in the upper part or in the lower part of the star, or depending on which tail is occulting your star, you can get a different transit signature because of that. This is also some food for thought, and I only realized that when we actually did this simulation. So I'll come now to my final slide. So just to conclude, The interactions between stellar winds and exoplanets, they can generate radio emission. And I suggested, or I discussed two types of radio emission, the one that we call the radio Bode's law. The stellar wind creates aurora in the planets. And then the second type was the induced emission coming from the planet towards the star. Then I discussed a little bit about how the evolution of Atmosphericscape occurs, and that knowing how the star behaves is important if you want to know how the future of a planet. The stellar wind can reduce Atmosphericscape. At first, I thought this reduction is going to be super significant, but when we started doing the simulations, we realized that this might not be so significant. But nevertheless, it is very important because even a small reduction in escape can generate a strong a signature or a difference in the Lyman alpha transit. And then if you look at variation in stellar outflow, so going from quiescent stage to CMEs, for example, you can affect this evaporation, at least momentarily. And just before I finish, we are planning on a symposium next year. So it is going to be a hybrid, very likely it's going to be a hybrid symposium, but hopefully we'll be able to meet in person soon. So this is a symposium where we are bringing people that are interested in stellar winds from low mass stars to massive stars, and also exoplanetary outflows. And we want to bring these communities together to kind of share the different tools we have and the different concepts we have, and maybe find some common ground. So if anybody's interested, this is the web page of the workshop. And the submission this is going to happen with the General Assembly in August next year. So the link for abstract submission is shown here below. So that's it, everyone. So thank you very much for your attention.
Thank you very much, Aline, for this wonderful talk. So now the talk is open for questions. Miguel will manage it. For doing a question, please raise your hand, like Rainer did, and then Miguel will allow you to do the question. So Miguel, the floor is yours.
Okay, thanks a lot for the beautiful talk, very comprehensive. Yeah, I really enjoyed. And yeah, I see already two people are raising their hands. I think Rainer was first. So Rainer, go ahead. Rainer?
Yes, sorry, I had to switch on the microphone. So thanks a lot for this talk, Aline. Fantastic. I really enjoyed it, and thanks for explaining everything so well. Nevertheless, of course, my physical background in this particular area is a bit weak. So I have two more questions. So the first thing was probably the easier one. So I was surprised that the stronger the stellar wind, the less atmospheric loss you have. Can I understand that physically, maybe in the sense that the primary driver of the loss is basically the EUV heating, and when I have a strong stellar wind, basically I create an external pressure environment that confines my atmosphere? That would be my first question.
Yeah, so that's a good question. So the idea is a bit of a hydrodynamic process. So you have two flows interacting. Now, if your atmosphere, imagine when the planet is evaporating, it crosses this what we call the sonic surface. So it goes from being subsonic, or having subsonic velocities, to supersonic.
Which was my other question, what the sonic surface is.
Okay, yeah, so that's what the sonic surface is. So essentially, the sonic surface tells us so imagine if you're running and you're shouting to someone else behind you. If you're running too fast above the sound speed, the person behind you will never listen, will never hear you. But if you are subsonic, you can actually transfer information back to this person. So the idea is similar for the planetary outflow. If the planetary outflow is supersonic, the stellar wind can do whatever it does. The bottom of the planet will never listen to what the stellar wind is saying. But if you take your stellar wind and you make it really, really strong, the point where the interaction can happen goes below the sonic surface. And when you are below the sonic surface, then you can you're right, XUVs is still the dominant force that is driving this material up, but now the stellar wind starts to tell the planet, stop sending mass. And that's where, if you disrupt the sonic surface, you can actually reduce the amount of escape. Now, when we had this idea first, we did all these models in 1D, but when you go to 3D, the dynamics are quite different, because now you have the night side that behaves differently. Maybe part of the night side will never see or hear the stellar wind at all. So the effect is much weaker than what I first had imagined. I don't know if this clarifies, but it's essentially the idea between two flows and whether the flow can affect the forces that are driving the outflow from one or the other system.
Very well explained. Thanks a lot.
Yeah, thanks a lot for the question. I also had this surprise and the same similar question for the part. So I think Pedro Amado goes next. Pedro, go ahead. Unmute you.
Hello, Alina. Thanks very much for this beautiful talk. I enjoyed it very much, and also it raised more questions than probably answers I could get from you, because my background maybe is not that related to what you are telling us. But I want to ask you questions to try to solve some of these doubts that I got from your presentation. Could you go back, please, to the slide where you show the Proxima Cen Alphen surface in your paper with together with a unique thing? Exactly. So two of the key parameters, if I understand this properly, are the magnetic flux and the mass loss rate. So you have here a mass loss rate for Proxima Cen, and also you have a magnetic flux that I believe was computed from semi-Doppler imaging. There was a value of around 200 Gauss for the global magnetic field. Going back to the paper, the data were taken during the maximum in the cycle, the magnetic cycle in Proxima Cen.
You're asking. So I don't know the answer to. I don't know if it was at the maximum of the cycle.
Yes, it was at the maximum.
Okay.
It was at the maximum. Yes,
Okay.
yes. The question that was a statement from the data. The question is now the mass loss rate. The mass loss rate is determined from Lyman alpha absorption, I guess.
Yeah, well, yes. In our case, this mass loss rate comes from our model. But you're absolutely right. There has been attempts using Lyman alpha observations to measure the mass loss rate of Proxima Cen, and they haven't detected it. So there is an upper limit on the mass loss rate of Proxima.
Okay, so in this case, does the mass loss rate this determination takes into account the possibility that closer to the star, the planet is seeing this higher mass loss rate because of the strongest field in the magnetic cycle of Proxima Cen, and then the Alphen surface may be bigger than in this situation.
Yeah, so I understand your question. So what will in particular in our models, what will change the Alphen surface is the map. So if you're looking at a different epoch and you had a map, a different magnetic field topology, and we run the simulations, we will probably get a different Alphen surface. So it's just what I said. So in the talk, this simulation is matched with this map. If we had a different magnetic field, yes, we can have a different result and a different mass loss rate. So the mass loss rate for us, so I did not go into the details of the model, but the idea is that the stellar wind is driven by mechanical waves. So these are Alphen waves. And these waves, as they propagate, they dissipate and they provide momentum to the wind, and then the wind blows. one of the unknowns in our simulation is how much waves we have. So we use here some solar parameters, but it is still something that we have to figure out. So if you change the amount of waves we have in the system, we can change the position of the Alfvén surface. So if an M dwarf, if the wind of an M dwarf cannot be treated in a similar way to the solar wind, then these simulations have to be revised. So we are assuming here a similar sort of physical mechanism to drive the wind. Now, in terms of the mass loss rate, the mass loss rate is determined by both the amount of magnetic flux we have coming from the ZDI observations, and also about this flux that I told you before, that is an unknown of the code. So if I want to put my planet inside the Alfvén surface, I would need to tweak these parameters. The thing for us is that when we tweak the flux, if for example, if you want to reduce the mass loss rate, the more we reduce the mass loss rate, yes, you can generate you can bring the Alfvén surface further out and the planet inside, but then the emission is very, very weak. So we could not get another. I don't know if that's I don't know if your question is leading towards why we don't see we don't predict emission while Miguel has detected emission of Proxima Centauri. So we could not find a good agreement on with our model, at least. We could not get if we reduce the mass loss rate, then we can't get the emission. I don't know if that's where we are, but I just to say, yes, there are unknowns in the model. We could think about tweaking this in the model. And again, I want to make the case that if we observe things, it will be good, because then we can constrain also our side of the modeling approach.
Perfect. Yes, this means that we still need to be talking to you about
yeah, that's right.
Yes.
Thanks, Aline.
Yeah, thanks, Alina. Yeah, well, if there is time, I'll come back to you, but otherwise we will chat about this later on. There are more questions, and I think next is Eva Villaver. So Eva, when you want to talk, unmute yourself.
Hello, Aline. Wonderful talk.
Thank you.
First of all, I have a question about how do you set up the hydrodynamic escape of the planet in the simulations? I mean, do you fix a value taking into account the UV flux from the star, or do you? Yes. Because modeling it with I mean, you cannot do both. You cannot model the interaction and you cannot model the escape from the planet. Yeah. So I wonder how do you deal with that, and if you have considered different scenarios, especially for the 3D simulations, because it's going to change everything.
Yeah. So in the 3D simulations, we started in the simplest way. So we started assuming an isothermal planetary wind interacting with an isothermal stellar wind. But then the idea would be that over the years, we're going to make the simulations more robust. So at the moment, our 3D simulations assume is no longer isothermal. So the XUV flux of the star provides the energy to hit the atmosphere. So you calculate the optical depth to these photons. So you know how much these photons energy is deposited at different points in the atmosphere. And then we take into account cooling. So we have Lyman alpha cooling, we have collisional ionization, but then we also solve for the ionization balance. We have collisional ionization, recombination. What else do we have? And we also take into account the advection. So but we still only have hydrogen. So for the outflow of the planet, that's how we do now. So we are solving an energy equation and the energy in the ionization balance. And for the stellar wind is coming as a boundary. So it's essentially the way we define what is the value that we put in the boundary. We use stellar wind models in a different. We calculate this in a different software, in a different code, and then we say, okay, that's the velocity, that's the density, that's the temperature, and then we fix these values, And when you turn on the simulation, it's almost like you had a constant inflow of the same values coming from the stellar wind.
Yeah, it's exactly the same way as I did simulations of the interaction of the wind from a star with the mass loss from with the interaction with the ISM. So it's interesting that we use exactly the same kind of approach.
Yes, and hence why we want to bring together all these people in this meeting next year, hopefully, because we understand it's the same code I use for the stellar wind here. It's the same code we use for the planetary outflow. So it's only different scales, but the idea is very similar.
Yeah.
The tools they can be transferred to different areas. Yeah, you're absolutely right. Yeah.
Okay, thank you.
Thanks a lot, Eva, for your question. I'm so happy that you are making all the questions I was thinking of so far. So yeah, I mean, you're doing a wonderful work. So now I think Jorge Sanz has a question. So Jorge, go ahead, unmute yourself.
Hi, hello, Aline. Nice talk and nice work. I like it a lot. I have a comment and a question. The comment is about the evolution of the XUV, the plot you have shown, which is coming from a work of people by Colorado.
This one?
Yes, this one. Yeah, it's just to let you know that if you put here the sun, it doesn't really match very well.
This is coming from Vienna, from the group of Manuel Guido.
Okay. So, well, yeah, I think it's the same. It's people of Vienna and people of Colorado, I think. Well, I'm not sure. So this is something to be careful about.
So the sun is in here.
Yeah, but I think the problem was if you separate by X-ray and EUV separately, it didn't work so well. So I don't remember exactly now how was the problem, but there was a problem with that. So also there is something to keep in mind, which is the solar cycle. The solar cycle can be even a factor of 50, and also the other stars have a cycle. So you may have some problems of variability. So I don't know how sensitive is this evolution model to your work. I'm not sure.
Yeah, that's a very good point. So the sun here is shown as max and min to illustrate the variation during the cycle. These lines here, they are done in a slightly, so they are a mix of empirical and modeling. So what they do, they use stellar evolution models to compute the rotation. And then from the rotation, they use X-ray rotation relationships. You know, you're obviously familiar with the plateau and then the decay. Yeah. And I think from the X-ray, then there is empirical relations that are used to convert from X-ray to UV luminosities. For example, using your relations, I don't know which relations they used here, but that's how they derive. I think they might have used your relations actually.
I think so, but this is something that we have to keep in mind. It has not been studied in the ultraviolet, of course. How the cycles.
No, it's very important what you said. The cycle would. You're absolutely right. So if you take a planet and you let it evaporates as the star is going up and down, you are going to have a change. So I did not show work here, but we did this study in 1D. So we got this XUV spectra coming from the sun using, it's called SEE instrument. So it's essentially, we are looking at a different spectrum from X-ray to ultraviolet from the sun. And we then said, okay, let's do the experiment, put hot Jupiter orbiting the sun and see how the evaporation changes. And at least using our 1D models, I think a factor during the cycle would only change a few times the evaporation rate. So it was not super strong. But of course it can vary depending on the mass of your system, or the mass of the planet, and also depending on how close the planet is from the star. But that was so it varies in the cycle, and usually we probably have to take into account this as an average number.
No, it could be that in the long term it doesn't really matter very much, because you may need just the average of the cycle, and that's okay.
Yeah.
And then keep in mind that this has been done with stars that has been observed once, and then the point would be either in the maximum, in the minimum. So that explains part of the variability, variations you see.
Yeah. We see the same variations when I plot magnetic field with age, and that's always I blame that the stars are cycling and we only have a snapshot.
Yeah. So and now that was just the comment. Now the question is, when you go and apply the XUV emission to your models, how sensitive is this to the XUV emission? Do you need just a bulk number of the X-ray luminosity or XUV luminosity, or do you need the spectral energy distribution that would make a difference or not?
Yeah, so in these 1D simulations we did, we used the whole spectrum because we had the sun. So it will make a difference, but we did not think it was, because we wanted to run for the whole cycle, the simulations, we did not think that the difference was so strong as to do this for all the points during the cycle or the solar cycle. I can point you to the paper. I might have it in my backup slides.
Rather than the cycle, I'm considering the balance between X-rays and extreme ultraviolet, meaning the spectral energy distribution.
Yes, I think, yes. So this is correct. Yeah. So if you are, it is going to change. Yes. So especially for young stars, where I think you have the relative contribution from X-rays to UV is stronger, that might affect. So what we simulated, we included this in 3D, but we don't have a spectrum. What we have is like an energy beam in X-ray and an energy beam in UV. And then we changed these energy beams. And what we demonstrated was it affected a little bit the mass loss rate, I don't know, a factor of 2. But the effect was actually more visible in the transit because the depths the X-ray photon or the UV photon penetrate are different. And therefore, it changes the ionization balance of the atmosphere. So this is a paper that has been submitted by Daria Kubishkina. So I don't have a slide here. But I'm hoping it will, I can send that to you once it is accepted, or even now I can send it to you.
Oh, okay. That would be nice.
So, are you happy with the answer, Jorge?
Yeah.
Okay. Thanks a lot.
Not too long.
Yeah. It was much shorter than the comment, so I was wondering maybe I should. Okay, anyway. So Camila Danielski is next. So Camila, when you unmute yourself, go ahead.
Hi, Alina. Thank you so much for the talk. I really enjoyed it. I had, maybe I missed something, but like just to confirm, are your simulations stopping to main sequence stars?
The stellar wind or the stellar wind simulations?
I'm more interested like in the stellar mass loss for exoplanets, but like all along the life of a star. So I was wondering like, maybe also, it's a question also for Eva, if we have any other models at the moment for stellar mass, planetary mass loss for white dwarfs, for instance, especially when they're hot. Maybe the stellar wind is less, the contribution is less, but I guess for extreme UV radiation, we might have an effect under that point of view. So. I was
So my short answer is no, I don't have any work on that area, but I agree with you. I think I suspect, I'm not an expert in white dwarfs, but I suspect that the wind was going to be less relevant, but then the energy might be more important. Yeah. Eva might know the answer.
Yeah, by allusion, I mean, we did simulations on that, and yeah, exactly that. I mean, the UV flux, especially during the early evolution of the white dwarf, which is when they are more luminous and hotter, is what is going to determine the evaporation of the planet.
Okay, so it's just the UV flux then. Okay.
It's the UV flux, yeah. The wind is not important because the UV flux is so big that completely dominates.
Oh yeah, exactly. Because like the temperature are very, like we go very high temperature. So I was wondering what was if there were any models exactly like.
Yes, I did some work on that.
Okay, I'll send you an email then. Thanks.
Okay.
Thanks, Alina, as well.
Okay. Thanks a lot for the question, Camila. So I think Manuel Lopez Puertas is next.
Okay, thank you. Right, good. Thank you very much. Thank you very much, Alina. I also join my colleagues. It's a wonderful talk. I have a question about, you probably know that we are recently doing the analysis of the mass flow rate of the planet by the analysis of the helium triplet emission. And I'm really worried about a little bit after your talk, because in order to infer the mass flow rate, we are using a very simple hydrodynamic model of the planet with no interaction at all with the stellar wind and so on. So I'm really worried about whether the values are really real. I mean, or it's just how important is the hydrodynamic model or the solar wind interaction to be in order to the value of the escape that we retrieve.
Yeah. So you invite me back in a year time and I answer that. But for now, what I suspect, so our code is purely hydrogen, but we can learn something in a post-processing, and that's something we are starting to work on. So if I take my hydrogen code and I assume that the whole thing is, I don't know, 90% of hydrogen atoms and 10% of helium atoms. If I assume this is constant with height, which might not be, but if I assume this is constant with height, what would be the signature getting helium 1? So that's one thing we are starting to implement. But in terms of the observations, you can correct it if I'm wrong, but I understand that most of the helium is seen closer to the planet. It's not as extended as the hydrogen.
Yes, in most of the cases, that's true. Right.
Yeah. So I think if you neglect the stellar wind in a scenario where the helium is closer to the planet, I don't think you're making a big mistake. No, I think you're probably good. I think the issue is when everything is very extended, because then the interaction happens much above, right? So it's in that region that if you neglect the wind, I think you could be you could be less accurate, and I think regardless, it's in all these models and observations. I know that there is a modeling coming to support to interpret, and I think it is for our work that any of those, they are really good because it can help us also constraining what we have and adjusting. So I think for helium it might be less problematic. It might affect, but it would be good if affected, because then we could learn more about the interaction. But I think on first order, I don't think it. But that's my guess. We have to learn this once we have more complex models.
All right, good. Thank you very much. Well, I think it's probably for some of the planets not much important, but for some of the Neptune we are looking at, they have a very extended atmosphere, and they might be important for them. All right, good. Thank you very much. Good.
Okay, thanks a lot. Is there any other question? If not, at least I would like to make one question. So maybe one thing. So Aline, wonderful talk. As you know, I became interested because of your work with Robert and your own works. And one of the things I keep being asked when I also present some of our results to others is about the magnetic field that actually is used. I mean, I'm talking about the planet-induced radio emission. So the second case where the relevant magnetic field is that of the star, not that of the planet. So that the one of the star is much higher. But of course, well, it could be that the magnetic field is actually the observation are telling us the magnetic field, the local magnetic field, not necessarily at the surface of the star, maybe at some height. So I was wondering which kind of geometries are you considering in your codes? It's just the dipolar geometry for the standard planets, open spiral. What is?
Yeah, so that's I can show you. This is one of my hidden slides that I'm glad that they have. So we use the geometry comes from work doing Zeeman Doppler imaging. So these works, they are essentially modeling they are reconstructing the large scale magnetic field of the star. So it could be, we talk here about, so just for comparison, this is the solar map. So it's very different if you have, the more resolution you have, the smaller the elements you can reconstruct. So for stars, we only have the very big, large-scale field. So we decompose these fields into harmonics, in spherical harmonics. So the dipole being one, and then the quadrupole, the octupole, and all that. So we only, most of the times we go to, I don't know, less than 10 harmonics for the stars. So we never see the salt and pepper structure that we see actually in the sun, if you look in the bottom plot. So our models take into account this large scale field, which is also the field that we believe is threading the stellar wind, is where it's embedded in the stellar wind. The smaller the field, they decay very fast, so they stay closer to the surface of the star. So having said that, so we don't impose like a single mode or just a dipole. We have the whole field. But the thing is, the further you are in general, the component that dominates is the dipolar, and eventually this dipolar field becomes radial. So the stellar wind, it opens up the magnetic field of the star. So at a certain distance, much above the Alfvén surface, the magnetic field is going to be more or less open. But then because the star rotates, it forms the spiral you just mentioned. So nothing is set a priori. In the model, we have the stellar rotation then makes the spiral. So things evolve. We have it incorporated in the simulation. So in first order approximation, a bit far from the star, mostly dipolar, and much further out, mostly radial.
Okay.
Or with some azimuth, well, with spiral.
Yeah. Okay. So I'm being informed that people are sort of going away. Yeah. And I would like to continue this discussion, but I think it's really time that we probably let everyone. We close this. We can continue now with off the record. If you just kind of stay for a few minutes. But I'll give the word to to René or Isabel. Thanks a lot, Aline.
Yeah. Thank you, Aline. Very nice talk. Very nice question session. So thank you very much for the talk. Isabel, do you want to say something?
I told you at the beginning that it was going to be extremely interesting.
That's very good.
I was right.
I hope it was useful. Thank you so much for the invitation.
I insist on the invitation, on a 3D invitation.
Yes.
like your models.
Yeah, it will be a pleasure. Yes.
Thank you very much, Aline.
Yeah, actually, so Liz, if you can just stay a bit more, but just just a couple of minutes. So I think as you can judge, many people are actually not doing. Are not radio astronomers. Many